Hello, Assalamualaikum warahmatullahi wabarakatuh. We are from Group 5 of Computer Architecture Organization from Session 2. Today we will present our group project. First, I will introduce our group member. First is myself, Muhammad Fahmi bin Muhammad Sharif, alongside with Muhammad Iqbal bin Muhammad Hatibi and Nurul Shahida binti Abdul Razak. And we will proceed to our introduction of our project to the next presenter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Iqbal bin Muhammad Hatibi. My metric number is CE200113. So my part is for introduction. In the modern world of computing device, the architecture of this device plays crucial roles in ensuring proper system design while considering potential hazard in the pipeline. The visual simulation of data hazard in the pipeline are rarely practiced or documented. This project is aimed to analyze the data hazard visually in the RIPS software to understand how they occur in the pipeline. So the pipeline design allows for the simultaneous execution of multiple instruction in a parallel manner, reducing the overall execution time. The pipeline consists of stages connected to form a pipe-like structure where instructions enter from one end and exit from the others. Each segment of the pipeline contains an input register followed by the combination of circuits that perform operations on the data held in the register. However, certain hazards such as data hazard can degrade the data processor performance. So data hazard occur due the dependence on prior instructions that are still in the pipeline. This hazard can be classified in the three types based on order to read in order to of read and write operation in the instruction. The pipeline refers to the process of obtaining and execution information from the processor in the orderly manners. There are three types of hazard in pipeline, such as structural, control, and data hazard. So there are three types of data dependence that leads to the data hazard: write after read, VAR, write after write, VAW, WAW, and read after write, RAW. Most data hazards occur in raw type, where an instruction attempts to read the register file before the latest data is updated in the write stage. RISC processors are commonly used to resolve this issue and follow a five structure, which is instruction fetch, instruction decode, and register file read. Instruction execution or address calculation, data memory access, and write back. However, in the architecture like MIPS, the implementation of data hazard is restricted. Specifically, the VAR, WAR, and WAW data hazard cannot occur in MIPS architecture. This is because the way the pipeline stage are organized, the memory operation occur in the fourth stage, and the instruction memory is read-only. So that's all from me. Thank you. Gitu bah. Boleh tak?
Okay, so for the literature review, first, the computer architecture, concept and evolution by Jared A. Blau and Frederick P. Brooks. This book provides a historical perspective on computer architecture, tracing the evolution of computer system from early machines to modern architecture. It covers key concepts such as instruction set designs, pipelining, memory organization, and input-output system. The author draws from their extensive experience in the field to provide valuable insight into architectural design principles. Next, computer organization and design. The hardware-software interface by David A. Peterson and John L. Hennessy. As mentioned earlier, this book provides a comprehensive introduction to computer organization and design, covering topics such as instruction set architecture, memory hierarchy, and parallelism. It offers insight into the fundamentals of pipeline design and its impact on computer performance. Uh, Furthermore, research papers on pipeline architecture, exploring academic research papers related to pipeline architecture, and provides further insight into specific pipeline design techniques and optimization. Some popular research topics in this area include instruction, scheduling, branch prediction, pipeline hazards, and memory access optimizations. Online research databases like IEEE, Explore, ACM Digital Library, and Google Scholar can help to find relevant papers in this field. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh. I am Syahida Binti Razak. My notice number is CE219. Okay, so I'm going to present for the simulation. And for the simulation, we are going to use RIP software to simulate the processor. Okay, so this is 5-stage RISC 5 processor. Okay, so first we're going to see the coding. Okay, first we'll get data, which is we will store the data in the memory. And we will use hexa, which is 09001, and we will store the word in memory A, and then 0 times 0002 we store in the memory B. Okay, that's next dot text, and then LW, which is load word. Okay, so load word A not A, which is load word memory will be A. We will register to the A not. Okay, next for the log word A1 B. So for the memory B, we will be into the register A1. Okay, next we go for the AD. AD, which is means we will add the register A0 with integer 5, and then we store the data into the A0. This. Okay, next AB, which is we will add the register A1 with the integer 4, and store the data into the register A1. Okay, then we will add the register A0 and A1, and then we will store in the A2. Okay, so we will see the so here we can see the pipeline. Here we can see the pipeline of the data. Is from instruction 1, instruction 2, instruction 3, 4, 5, 6, and 7. Okay, which is it is by sequence, which is fetch, decode, execute, memory, and write back. Okay, next we will for the non-pipeline diagram. Okay, so for non-pipeline, we just same with the pipeline. But what's different is, okay, for non-pipeline, we will go to cycle 0, 1, 2, 3, 4, and we will go to first fetch, decode, execute, memory, and write back. And we will go for it, and we just will follow the flow lah. For instruction 1, and then we go for the instruction 2, until write back. And then we will go back for the fetch, decode, execute, and memory, and write back. But for the number line, we will have 29 cycle. It is different with the it is different with the part 9, because with the part 9 we will just use 11 cycle here. Okay, so for conclusion for the result, part 9 diagram, the part 9 is more efficiency than the number 9. Okay, next we will go to see what is actually the hazard is in the part 9. Okay, so for the hazard, we will try to do the this. I will copy this, and then I will place it under the load word A9. Okay, so what will happen if we put the AD under the load word A9? Okay, so refresh this. Okay, so we can see that at the cycle number 4, there is a hazard here. Why there is hazard? It is because it not have enough cycle to do, and it will clash with the what we call with the instruction before. Okay, so next, what to do if we have hazard, right? So we will put under the load word A0 and OP, which is means in operation to eliminate the hazard. Okay, let's see. We refresh this and this. Okay, so we don't have any hazard here, as it have enough cycle to do the instruction. Okay, so that's all for me. Thank you.
As for the conclusion, we know that RAT is widely used as an educational tool to teach students about computer architecture and RICV IC. RAT also allow user to simulate the execution RICV programs and enable user to model how RICV program would run. And also the user can effectively debug and analyze their code since it provides a graphical presentation of the processor state. With the aid of this capability, user may have better comprehend the inner working of the RICV architecture and spot any potential mistake or performance bottleneck. And lastly, Bribe is a very valuable tool for developers and educators working with RICV, as it can offer a range of features and capability that facilitate code development, debugging, and educational purpose. There are several recommendations that we can give based on our experience using the RIPE. And first one is the RIPE maybe can expand the simulator's capability to allow the user to perform detailed performance analysis of their RICP programs. And also the RIPE's developer can also improve the debugging and tracing capability of the simulator. And finally, the developers should continuously update and refine the simulator based on the user feedback and community contribution. That's all for our group. Thank you.